Welcome back after a longer break. From now on, I'll try to keep up the pace of making new content because I'm really keen to make progress building my Intel 8188 computer. There's still lots to do, not only in terms of the hardware, but also the software. Last time I was talking a lot about the Raspberry Pi Pico microcontroller because it is going to be the main peripheral in our computer. We briefly tested its communication on the CPU's data bus successfully. In this video, I'm going to introduce a very important ingredient, allowing us to start implementing this peripheral on the Raspberry Pi Pico. But let's start from scratch. This is as trivial a program for the Pico as possible. It's a simple hello world whose only task is to blink the green LED on the Pico board. Let's have a look at it. This program, as well as all the other presented in this video, are on my GitHub page for you to easily start your own projects from. So here we have our main function. That one, Pico default LED pin, is defined in the Pico SDK, and that points to the green built-in LED on the board. So what we do first is we initialize the GPIO, set it as an output pin, and then we enter the infinite loop, which simply switches the GPIO pin between 1 and 0 with 1 second. 1000 milliseconds is 1 second in between. So the effect is quite obvious and simple, and you can look at it now. Nothing to really write home about. You can use it as a starting point for your own designs. I included the CMake file, which configures everything, and it's ready to be used and compile. Let's have a go. This whole project is ready to be used in the environment, which is configured according to one of my recent videos. Please have a look at my channel and you can find a step-by-step instruction about how to configure all the tools required to build this project. This example is as simple as it can get, just one LED blinking using one GPIO pin. But programming for microcontrollers in real life gets quickly more complicated than that. Usually we need to care about multiple things at the same time. There are some sensors on the I2C bus, some other devices on the SPI, like in our case, where we will be using SD card as the hard drive in our Intel 8188 computer. There is an analog to digital converter used to process some analog signals or simply to measure the voltage of the battery in our battery-powered device. There could be a serial port used for communication, and most likely some GPIO pins are involved as well. Usually there is an infinite loop in the program where we handle all the devices and protocols. It may be simple if all we have to do is to change a state of some GPIO pins, which is instant, and we can then switch over and handle another device momentarily, but often the tasks we perform may take some time. Then we usually use interrupts to carry on when the task is finished. In such cases, we need to switch to another piece of code to do some other work, which quickly gets messy as you need to remember where you were to be able to carry on when finally the long-running communication raises the interrupt. It would be much simpler if we could handle each device logically in one place, one function, like we often do when programming for big computers, where the operating system like Windows or Linux offer multitasking execution. Usually in cases like that, we start a new thread for each task and we rely on the OS to do the switching between them behind the scenes. It would be so much easier to implement all of these if we had a multitasking API available on our Pico. And that's exactly what FreeRTOS offers. FreeRTOS is an open source, real-time operating system for microcontrollers. It may run even on devices having very small amounts of flash or RAM memory. It offers multitasking execution, timers, synchronization primitives for thread-safe communication between the tasks or interrupts known from the big OSs. All of these objects can be created dynamically or statically, depending on the available resources on your microcontroller. Every aspect in FreeRTOS is fully configurable. You can switch, for example, every API on and off, depending on your needs, which can save the usually very limited amount of flash memory in your microcontroller. It sounds like a perfect solution for our multi-I/O device in the Intel 8188 computer, where we will have to handle several different devices. That's the reason for this video, to explain why I'm going to use FreeRTOS in the multi-I/O code from now on. You may think, oh, a whole operating system, this is going to be complicated. But adding it to your project is actually very simple. You only need to check out the FreeRTOS kernel repository, add one line to your project's CMake file, add one configuration file where you can configure every aspect of the FreeRTOS, and then simply include a few header files in your code. I've got two projects here. The one you've already seen and the new one doing exactly the same thing, but this time under the control of FreeRTOS. Let's look at the differences between them one by one. The first one is this new folder, which I called external. It contains the FreeRTOS kernel source files. If you check this project out from my GitHub page, and you initialize submodules, you will automatically get this folder downloaded from the FreeRTOS repository. So it will be ready to be used. You don't need to really worry about it. The next change is to the CMake file. Let's have a look at the differences apart from the changing the name of the project. We have this additional line which includes the FreeRTOS for the RP2040, which is the microcontroller on our Pico. So that's the only really change which is required. The path points to the FreeRTOS kernel within our external folder. This line helps FreeRTOS kernel to pick up our configuration header file, which is in the current directory. And the last difference in the CMake is a few additional libraries. FreeRTOS allows to switch the task and run all the tasks on both of the cores of the Pico microcontroller. Remember, it is a double core microcontroller, and this library contains all functions from the Pico SDK, allowing to use the second core as well. And the two libraries here are, as you can see, the kernel of the OS and the heap implementation. There are a few, but they are recommending using the heap number 4, and this is obviously for the dynamic allocation of memory in our code. So that's all in the CMake. That's all we need to do to start using FreeRTOS. And now the most important changes are obviously in the code. So let's look at the main.c file. So previously we had this main on the left hand side. We have this main function which contained our GPIO setup and the loop blinking the LEDs. Now it is not in the main. As you can see, we created the LED task function, which holds almost exactly the same code, but we'll get back to it in a minute. We also have some other two functions which our OS requires, but we'll get to that in a second. To include files, the main one, FreeRTOS, and the task, because we are using functions to create and use the tasks. Now at the bottom we've got the main function. The first call in the main function is the stdio init_. That's got nothing to do with FreeRTOS. That's a usual function call in the beginning of your program for Pico if you want to use the serial port as your printf output, so you can just print out anything you want for debugging or looking what happens in your program to the serial port, which could be connected to your computer, and then you can just see on screen what is happening step by step. So this is good for debugging. I just left it just in case I wanted to use it later. This is our hello world starting point, which you also can use if you're interested in programming for Pico. So I left it here in the main function, even if I'm not gonna use it in this program. The next line is quite interesting. It is the first call to our FreeRTOS program. And that's to, as you may expect, it is to create a task, our first FreeRTOS task. First parameter is the most important one. It's the name of the function which will be run under this task. The next one is the task name, and there are some settings which you can also configure for this task, like its stack size. Then you can pass a parameter to the task, which is a pointer type, and tasks have priorities in FreeRTOS. So you can prioritize some tasks which are more important to you to be run more often. We're just using the default idle priority. And in the last parameter, you can get the task handle back from the OS. Similarly, like in big OSs, if you want to call some functions on the task, you need its handle. We're not using this here, it's just a very simple example. So that's where we create the task for blinking our LED. And as you can see, this is the name of the function which I just defined here, up here. The void star PV parameters is the variable which you can pass on to the task via this fourth parameter. We're not using this as well. And the body of the task is very similar to our old main function, with one only difference. As you can see, we used the Pico SDK sleepms previously to delay execution of the program. Now we've got a vtask delay function. That's a FreeRTOS function which does the same thing, but in a different way. Because here, in the old program, we just kept the CPU busy while it was waiting until the time has passed, while vtask delay just signals the OS, our FreeRTOS, that we want to wait a period of time so you can use the CPU to run other tasks in the meantime and call us back, return from this function when the time has passed. So it's a very interesting difference, because this doesn't waste the CPU time, which can be used by FreeRTOS to run multiple different tasks at the same time, because we know that this task won't be needing any CPU attention for, in this case, 1 second. The parameter is passed not directly as a number, but as you can see, that's a macro which translates the number of milliseconds to system ticks. The system tick is configurable for FreeRTOS in the configuration file. Okay, so let's have a look what happens in the main after creating the task. This is the FreeRTOS function which you enter if you want to start running the OS. So you can create task or multiple tasks, and then you enter the OS. This function never returns. The last call is really not required here. It's a kind of fail-safe. Because, as I said, the task start scheduler should never return, so this function has no practical chance to be called. But what it does is just holds the CPU, because it is treated as a non-recoverable error if it enters. So that's the main function. We have also these two functions here defined for FreeRTOS. And these are called when something bad happens. So the first one is called when there is a detection that the stack was corrupted and we can't carry on. So what it does is this displays using the printf, so the console out, this message giving the name of the task which failed. And we can see this using the serial port, which we just initialized here, by the way. The other function is called when something bad happens in the dynamic allocation of the memory, which also prints this message out, malloc failed, and holds the whole system because it can't carry on. If you don't use dynamic memory, of course, you would not need this function at all. So let's have a look at the configuration file, which you can turn on and off dynamic memory allocation, for example, and many other things. This is the FreeRTOS config.h. It contains multiple macros which define very many aspects of the FreeRTOS. Here, for example, I just randomly scrolled at this line, which is the tick rate, which I mentioned. So by default, it's 1000 Hertz, so 1 millisecond tick. I'm not gonna spend too much time explaining here every setting, but there are multiple settings which I preset for some sensible values for the Pico, like another random pick. That's the total amount of RAM which will be used for the dynamic allocation for the heap, which is 128 kilobytes. You can change it to your needs. There is the check for stack overflow, which operating system does. And if it finds that something was wrong, it will call the function which we just saw in the main.c. There is a definition how many cores will be used, which I defined as 2, which means that FreeRTOS will use the other core in parallel, so it will use both cores to switch between the tasks. There are 2 definitions of that, and the reason for that is that at some point FreeRTOS changed the name of this macro, but the Pico SDK is still using the old one. So just in case, I defined both. And there you can include all the features of the OS which you need, and you can exclude those which you don't need. Obviously, all features take some space in the flash memory. So if you're designing for some very little 8-bit microcontroller, you may want to turn off some of the options. That's all the changes required to start using FreeRTOS on the Pico. Finally, let's modify this simple project to accommodate multiple tasks. Let's blink 3 LEDs this time, each in a separate task. I created a copy of this Hello World project and called it Blink FreeRTOS this time. Let's open it in the VS Code and have a look. It's exactly the same as we just saw, so let's modify it to run multiple tasks this time. So we're gonna need 3 of these functions. Let's just simply copy them. 3 copies. Let's call them LED1 task, LED2 task, and LED3 task this time. The first one will still be using the green LED on the board, and the other 2 we just need to define some, let's say 26 GPIO number 26 for the LED2 task and 27 for the third one. So we've got 3 functions running an infinite loop which blinks 1 LED each. Now we just need to create 3 tasks. The first one changed its name to LED1 task this time. Let's change the name as well, why not? And then just add 2 calls to task create. But remember to change the name of the function in each call and the name of the, that's 2 and 3. It doesn't really matter, it's just informational. Okay, and that should work. Let's try to build it. It will take a while. To make it more interesting, let's change the times in each task. So the first one will leave 1 second on and off. let's change this, for example, to like 300 milliseconds. And here, let's do this non-symmetrical, like 100 and 700. Okay, now I think we just need to build the whole project and send it to our Pico. And by the way, that's the reason why I put the Pico on the breadboard, and that's because obviously I need to add 2 more LEDs, GPIO port number 26 and 27. That is our 3 LEDs, which are blinking using 3 separate tasks of FreeRTOS. Of course, FreeRTOS is much more than just the tasks. It also offers, for example, timers, which let you run a piece of code periodically, or synchronization primitives known from the big multitasking operating systems like mutexes or semaphores. It also offers structures for communicating between the tasks like queues, message buffers, or streams. I made this video only to introduce FreeRTOS to you and explain why I am going to use it in the multi-IO peripheral in our Intel 8188 computer. Please refer to my GitHub page if you would like to use these programs as a starting point for your own projects. If I got you interested and you would like to know more about FreeRTOS, let me know in the comments and I will be more than happy to go into details and explain all the available APIs in a separate video. If you don't want to miss it, please do subscribe and leave a like. Thank you very much for doing so, and I hope to see you next time when we start implementing the firmware of the multi-IO using FreeRTOS. We're going to start by accessing an SD card, which we'll use as the hard drive in our Intel computer. See you there!